This is a video for MEI Core Pure Mathematics, second order differential equations 3, modeling with second order differential equations, 3.1 simple harmonic motion. Simple harmonic motion occurs in a number of places. You might see it with a mass bouncing up and down on the end of a spring. So if you imagine you've got a spring like this with a mass hanging on the end of it, if you pull that mass downwards and let it go, then the mass will bounce back up until it's above where it started, and then it will start to fall back down again. And this up and down oscillating motion is an example of simple harmonic motion. You can tell if you actually do this experiment with a physical spring and mass that as you pull this down, the tension in the spring increases, and therefore the force with which it will be returned back towards the center is greater, and when released the acceleration will be greater. Other examples of simple harmonic motion include a simple pendulum, where you have a mass on the end of a string and it's oscillating backwards and forwards, or indeed the piston in an engine which is going up and down whilst a crank revolves below it. So all of these, and there are many other real-life situations, have an oscillating motion that can be modelled by this equation. d2x by dt squared is equal to minus omega squared x. So the acceleration is directly proportional to the distance from the centre of motion, and indeed is in the opposite direction, so it's towards the centre of motion. So let's have a look at solving this differential equation for simple harmonic motion. So let's rewrite this differential equation first of all. d2x by dt squared plus omega squared x is equal to 0. And this is now in our normal format, so we can form the auxiliary equation. That's going to give me m squared plus omega squared is equal to 0. That's going to give me that m squared is equal to minus omega squared, which tells me that m is plus or minus omega I. Now that gives me a general solution of x equals some multiple of cos omega t plus some multiple of sine omega t. And notice that it's x equals, we've got x is the dependent variable on t here, so it's x and t that we've got in our solution. Now we already know that if we have some cos thetas plus some sine thetas, we can transform that into a single sine curve of this form, r sine theta plus alpha. So if we use this in this solution, we get that we can rewrite the general solution as x is equal to some multiple of sine omega t plus something, and I'm going to call that something epsilon. And so there's our general solution for simple harmonic motion. There's that written up so that you can read it a little bit more easily. There's the original equation. The auxiliary equation gives rise to this pair of solutions, which tells us that the general solution will be of this form. There's the confirmation about the rewriting of multiples of cos and sine in a single sine wave, and there is our final general solution. So looking again at this solution, if I differentiate it, I'm going to get dx by dt is equal to a omega cos omega t plus epsilon. And in fact, we've seen that we can use a dotted notation for derivatives with respect to time. So I'm actually going to write this as x dot is equal to a omega cos omega t plus epsilon. And differentiating that again, I get x double dot is equal to, when I differentiate cos, remember I get minus sine, I'm going to get an extra omega, so I'm going to get minus a omega squared sine omega t plus epsilon. But if you look at this thing, this here combined with this is just x, a sine omega t plus epsilon, and therefore this thing tells me that x double dot is equal to minus omega squared x. Okay, let's take a look at a dynamic plot for this. This is set up so that we've got x is equal to a sine omega t plus epsilon, and at the moment a is 1, omega is 1, and epsilon is 0. So I've just got a normal sine curve. It's oscillating once over the range 0 to 2 pi. It's oscillating between 1 and minus 1, and it starts at 0, 0. Let's have a look at what happens as we alter the parameters. This thing here, a, as I alter it, as it gets larger, the sine wave gets taller. And in fact, it's just the multiple for the sine wave, so if it's set at 3, it oscillates between 3 and minus 3. We refer to a as the amplitude of the motion. Omega refers to the frequency of the motion. At the moment, I've got a single oscillation in the period 0 to 2 pi. If I increase omega up to 2, you'll see I get 2 complete oscillations over the range 0 to 2 pi. And in fact, 2 pi over omega will give me the period of this motion, in other words, how long it takes to complete a single oscillation. And finally, let's have a look at epsilon. Epsilon is 0 at the moment. As I increase epsilon, you'll notice that the sine curve is merely stepping, well, effectively stepping backwards. 1.6 is almost pi by 2, and what I've now got is a cos wave. And the phase shift, as we call it, it's just whereabouts on the sine curve you start. The phase shift epsilon will alter whether it starts early or late compared to a sine curve. So here around 3.2, it's almost pi out of phase with the original sine curve. So in summary, for simple harmonic motion, this is the second order differential equation. It's telling me here that acceleration is proportional to distance, and in fact it's in the opposite direction to the distance, so the acceleration is proportional to minus x. Its general solution, and this can be quoted, is x is equal to a sine omega t plus epsilon, and let's look at the bits of that. A is the amplitude of the motion. It affects the height of the wave. Sine t is periodic with period 2 pi, so it has a period of 2 pi over omega. Epsilon is called the phase shift, and it's the amount by which the wave has been translated either left or right. If epsilon is positive, then the wave has been translated left by epsilon over omega. The next video in this sequence is 3.2 damped oscillations.